Okay, so if you're a site engineer, you know that one of the most critical skills you've got to have in your back pocket is designing a solid cold water system. In this explainer, we're going to break down that whole process, step by step, using the major plumbing codes that are, let's be honest, your Bible out in the field. So, let's just dive right in.
I mean, really think about that for a second. You've got a massive skyscraper. How do you make sure that the tap in the penthouse has the same great pressure as the one in the basement coffee shop? It sounds like a huge headache, right? But it's a puzzle we solve every single day with some smart, systematic engineering.
And the secret? Well, it isn't some kind of magic. It's a method, a really clear, repeatable three-step process. Our guides on this journey are the Saudi Building Code, the SBC, and the International Plumbing Code, or IPC. And you got to think of these codes not as a bunch of annoying rules, but as the actual playbook for getting this right.
All right, so here's our game plan. We're going to start with the big picture, the design objective. Then we'll get into the nitty-gritty with the three core steps. First, calculating something called fixture units. Second, finding your peak demand. And third, sizing your pipes. And to make sure it all clicks, we'll wrap it up with a real-world example so you can see it all in action.
So what are we really trying to do here? What's the main goal? Well, it's to take what is essentially a jumbled of individual taps, toilets, and showers and engineer them into one single, cohesive cold water network that just works perfectly.
This pretty much sums up the whole philosophy. First, we have to standardize everything. We convert every fixture into a value called a fixture unit. Then, we use some proven hydraulic formulas to do the heavy lifting with the math. A huge part of this is managing pressure loss, making sure water actually has enough oomph to get where it's going. And the foundation for all of this? Sticking to our codes like glue, the SBC 701 and the IPC 2021. Okay, let's get our hands dirty with the first practical step. Before you can design anything, you have to understand the total demand on the system, what we call the load. And that's where fixture units come into play. So what on earth is a fixture unit, or FU for short? Honestly, the best way to think about it is like a universal currency for plumbing. It's just a single number that the codes assign to every type of fixture, a sink, a toilet, whatever, that represents how much water it's likely to use. It's a really clever way to simplify a super complex system. So your very first job is to do a takeoff. You literally count up every single fixture in the building. You look up its FIU value in the code tables, multiply, and then add it all up. You can see it right here. 10 water closets, and the code says they're 4 FIU each, so that's 40. You do that for everything on the list, and you get your grand total. In this case, it's 81 fixture units. That's it. Step 1 is done. Okay, we have our total FU number. But what do we actually do with it? Well, now we have to translate that number into something an engineer can really use, like flow rate and pressure. And that brings us to step 2. Now, here's where the codes are really smart. They know the probability of every single person in the building flushing their toilet and taking a shower at the exact same time is, well, it's basically 0. So they give us these probability curves. You just take your total FU, find it on the bottom of the chart, go up to the curve, and then over to the side to find your realistic peak demand flow rate. We call this Q. This is the actual max flow your system needs to be able to handle. Now, to talk about pressure, we've got to talk about the famous Hazen-Williams formula. I know it can look a little intimidating at first, but let's just break it down. HF, that's what we're solving for, the pressure you lose because of friction. L, that's just how long the pipe is. Simple. Q is the flow rate we just figured out. D is the pipe's diameter. And C is just a number that represents how rough the inside of the pipe is. And here it is, in all its glory. Now that we know what all those letters mean, it's really just a plug-and-play calculation. Trust me, this formula is the absolute engine of hydraulic design. You're going to get to know it very well. So here's the crucial takeaway, the whole reason we do this. We run this calculation for every single section of pipe in our system. Why? Because it tells us exactly how much pressure we're losing along the way. That's how we can guarantee there's still enough pressure left when the water gets to that last tap at the end of the line. It's all about managing that loss.
All right, we've quantified the load, we've calculated the flow and pressure. Now it's time for the final step, where we actually make some physical decisions. It's time to size the pipes.
And this right here, this is probably the single most important rule in pipe sizing. The velocity of the water inside your pipes cannot, I repeat, cannot exceed 3 meters per second. If it goes any faster, you get that awful whistling sound in the walls, and over time, it can literally erode the pipes from the inside out. This number is our absolute hard limit. So how do we make sure we stay under that limit? Well, you've got two simple tools in your toolbox. If you've already picked a pipe size and you want to check it, you use the formula on the left. But if you want to figure out the minimum pipe size you need to get the job done, you use the formula on the right. It's this constant back and forth of calculating and then checking your work.
Okay, theory is great and all, but let's see how this actually works in the real world. We're going to apply our three-step process to a project you'll see all the time, a residential villa. So let's walk through it. Step 1, we do our fixture count, and boom, we get a total of 24 FU. Step 2, we use the demand factor from the code, do a quick calculation, and get our peak demand, Q, of 2.16 cubic meters per hour. And finally, step 3, we plug that flow rate into our velocity formula, and it tells us we need a main supply pipe that's about 50 millimeters in diameter to keep things running smoothly and quietly. See? When you break it down, it's a completely solvable problem.
So, let's lock this in. Your workflow for any cold water system project is always these three steps. 1. Quantify the load in fixture units. 2. Calculate your flow rate and your pressure loss. 3. Size your pipes to keep that velocity under control. Quantify, calculate, size. That's the heart of the whole process. You know, we've just walked through this really methodical, systematic process that guarantees efficiency and performance inside the walls of a building. It prevents mistakes, and it ensures quality. So, the final thought I want to leave you with is this. What kind of clear, three-step process can you design for your own work out on site to make sure that your efficiency is just as buttoned up and just as reliable?